overall system consists of a containment system for the egg, a Wi-Fi-based deployable parachute, a non-Newtonian fluid covering, and some cotton padding. The egg is floating inside the non-Newtonian fluid for protection, and the container is on top of some cotton. The parachute is contained inside a container on the way up and deployed once it reaches the hangtime point by an observer over Wi-Fi. The parachute pops out and helps ease the landing.
One of the most visible systems on the lander, the parachute system is also one of the most important. Inside, it contains the parachute on a pusher plate which rests on a pair of elastic bands. These create the push force required to eject the parachute. To deploy, the servo motor is turned, allowing the lid to open. The elastic force from the rubber bands then proceeds to launch the parachute into the air. The first physics concept that comes into play during the launch is reducing the energy lost due to air resistance. By compressing the parachute into a smaller space, we can reduce the cross-sectional area of our lander, therefore reducing the amount of energy we lose due to air resistance on the way up. By doing this, we can get a large increase in our maximum height while maintaining the same amount of initial energy. This makes it significantly easier to maintain the required height while still having the ability to use a parachute on descent.
By looking at the math, we can easily see the advantages of the deployable parachute. When the lander is on its way up, a parachute would naturally fall into a downward state as seen here. This means that air would get caught underneath the parachute. If we assume the parachute gives us about 40% energy loss on the way up, using our conservation of energy concepts, we can see that with an approximate launch speed of 5 meters per second, we'd only reach a height of about 77 centimeters. However, without the parachute, we can safely assume we have about a 15% energy loss. Running the same formulas again with the new figure results in a height of about 1.08 meters, a significantly large advantage.
The second physics concept that comes into play during our launch is the parachute. By having the parachute create friction on the air, as well as drag on the way down, we can create an upwards force. This allows us to reduce the effect of the gravitational force, which in turn reduces our acceleration. By reducing our acceleration, we can reduce the momentum going into the impact. The less momentum, the less damage the impact will do to the egg.
To demonstrate the effect of the parachute, we start with a simple free body diagram. You can see here that the force of gravity outweighs the force of air resistance. If we use our equations, we can see that this means that we will have a positive net force. This means that we'll have a downward acceleration leading to a higher momentum on impact. In these equations, we can see that air resistance is negatively proportional to acceleration, which is directly proportional to velocity, which is directly proportional to our momentum. This means that by increasing our air resistance, we can decrease our acceleration. In result, that decreases our momentum on impact. This decrease in momentum will reduce the amount of protection we have to add to the egg.
Elasticity is the ability for an object to store and release back its energy. Elastic objects store energy after an impulse by changing shape and rebounding back to their original shape to get the kinetic energy back in the opposite direction. In this process, some energy is lost due to heat. Our contraption uses this principle by having elastic objects to absorb the energy when the contraption hits the ground and be able to rebound back and lose some of that energy to heat, as well as extending the time of the forces. The contraption is cotton that acts as an elastic device that will deform when the contraption hits the ground. It will reform back upward. This elasticity is useful as some of the energy is lost to heat and the force gets spread out over a longer time, leading to less damage. The non-Newtonian fluid is also elastic, helping to keep this effect more powerful by having the cotton and the non-Newtonian fluid helping with this effect. Force distribution is a concept of how a force can be distributed over a large surface area to lower damage to specific points. When a force is hitting one sole point, this point is a point of weakness, as it cannot handle all the force on it. Objects are more powerful when forces are applied equally throughout the whole surface area. The egg will be completely submerged in the fluid, allowing the egg to get an equal force on all sides. The non-Newtonian fluid distributes the force over more surface area, reducing the impulse on any one specific point, even though the total impulse remains the same. Due to its fluid nature, the non-Newtonian fluid will form a perfect contour, maximizing the surface area. The equal forces on all sides also help to keep the egg's yolk from flying up and breaking through another area that has less inward pressure. This is important since the yolk is one of the most common ways an egg can crack. This is why divers make a point with their fingers to break through water. When doing so, they are putting a large force on a tiny surface area to break through the water. If they instead put their force on a larger surface area, such as a belly flop, the water would not break as quickly and would result in them getting a large force backward. When there is a force surrounding the entire egg, when the yolk tries to move around due to continuing in motion while the entire object stops, the yolk can't go anywhere because if it tries to break through the egg, there'll be another force downward into the egg. So the yolk's force will be compensated against. Impulse is the equivalent to the force over time. When the same force happens over a shorter time, the impulse is stronger. When the same force happens over a longer time, the impulse is weaker. A larger impulse will lead to a more damaged egg, as the change in momentum will be so sudden. Overall, the same change in momentum happens, but it gives the egg time to absorb that energy. Our contraption uses a non-Newtonian fluid made from cornstarch and water to slow the egg's sudden change in momentum when it reaches the ground. This fluid will allow the egg to move through the fluid slower than it would in air, leading it to have a much lower impulse. This fluid is much more viscous than water, but still fluid enough to allow the egg to move around right after impact. Because it is more viscous than water, it will allow the egg to travel for a longer time from the same force, lowering the impulse. A high impulse will make the egg yolk immediately move to the top of the egg and crack straight through it. Lowering the impulse will make that behavior not as sudden. The egg yolk will not have as much force when it reaches the top of the egg. The non-Newtonian fluid does work. Here you can see a video of the egg falling in a container filled with this fluid. The egg survived after many drops, and only the container breaks. Here is the egg being dropped onto the non-Newtonian fluid to demonstrate the elastic properties. The egg survives even when the egg is thrown very hard at the substance. The fluid protects the egg so much that it ends up actually spreading the force into the container, and the container ends up breaking instead of the egg. Here's how little force is needed to crack an egg on the pavement. One thing I determined from this testing is that the egg survives most when it is dropped onto the bottom instead of the side. This makes sense since as the force reaches a point closer to the tip, it gets easier to crack the egg. If force touches the tip, it has very little surface area to spread around in, causing the egg to crack in the location of weakness. The tip is going to be the weakest location since it has the least surface area per volume.